Good. Happy Sunday, everybody. Good evening. I was I was fidgeting with my connection here. I think I mentioned that I'm working from out of town, and it's a very strange place here. The Wi-Fi where I'm staying is virtually unusable. So I was attempting to tether here, which I have done. Kindly asking if we would have somebody, confirm if you can hear me just fine. So that we start. Thank you very much. We appreciate the confirmation. Okay, so like I said, right, the reason we are having this class is because we could not have class on Friday. We had an assessment, and we're trying to avoid a situation where we actually we miss classes here because we don't have the luxury of missing classes. We have we have a month and 2 days left, is it? Because last day of class is supposed to be the 17th, right? So exactly, thing. And by my count here, you notice here that we have 1, 2, 3, 4, 5. So about 15 lecture series remaining, which should probably take us to a stage where we'll be able to finalize everything, right? But we just don't want to play around with time here, especially that there's probably a whole bunch of holidays here. I'm not really sure if we're affected. I think we are because we have Good Friday and all those things, right? So we're probably going to miss a class or two or something. I think there's also an IMSA open day or something like that. But anyways, on with it. Right. I wanted to remind us that we have a quiz, okay, which is based on the current lecture series, so lecture series number 5. I sent email to that effect, and I mentioned that this quiz ideally is scheduled for not this week but next week. So we are writing this quiz on the 27th. Hopefully you guys have taken note of that. Okay. Yeah. So just take note of the quiz time. And then also more importantly, I mean, this lecture series is probably just going to be a very short one. I would want to get us to a stage where we set the stage, pun intended, for our discussion of transformations, right? If that makes sense. So we just want to finish off our discussion of the cube, which in our opinion was somewhat interesting. I think we're trying to put together these basic concepts that we've been discussing ideally, right, when it comes to drawing using these primitive types. So anyways, we had actually started our discussion of how exactly we would render that 3D cube, bearing in mind, of course, that we are rendering it on our 2D screen, is it? So in essence, it's almost as though, not almost as though actually, what we are seeing as the output is a process of rasterization ideally. But anyways, so I'd walked us through, I'd say walking us through the code, right? The code ideally that renders this, right? We are, for the benefit of those of us that would have forgotten what exactly it is we are busy with, I'm just going to, I'm going to render this cube of ours, cube NumPy, right? So what we are doing is we are essentially rendering this thing, right? Ideally, and it turns out that the issues to do with how rotation actually works, what's actually happening behind the scenes, is the stuff we're supposed to cover in lecture series number 6 when we start looking at transformations. Remember those affine transformations we spoke about, right, during our discussion of the logical graphics pipeline, right? So translation, scaling, rotation. There's quite a bit of rotation going on here. There's some translation as well. But also it turns out that there are other, transformations that generally would not be discussed in depth. So things like shearing and reflection ideally. But anyway, so we're trying to understand exactly how this thing is being rendered. And our goal really is to just gain an in-depth understanding for the purposes of exercise number 5 of how these 6 faces are rendered, is it? And we said that the starting point is in the current slide here where we're defining. We realize actually that we need a total of 8 vertices or vertexes, okay? And so in our code, we are defining them as a 2D NumPy array, okay? Now, it turns out that each vertex is defined with not just the position X, Y, Z, but also the color. And we're simplifying the color. We're omitting alpha, so we're just including R, G, and B, right? Is the reason why, if you look at V naught here, we have a total of 6 attributes, is it? X, Y, Z, R, G, B, okay? In an ideal case, actually, when you're using, modern day OpenGL with shaders, it's a core OpenGL, not really legacy mode or immediate mode, which is what we're looking at. You'd be defining these things in a slightly different manner. In fact, interestingly enough, you define them in a single array object ideally, because the GPU ideally expects a stream, right, of data. The reason why I would want to encapsulate, these vertices in a 2D object is because it's a lot easier for us to understand idea. But anyway, so we have these 8 points, right, defined in a 2-dimensional NumPy ND object. Okay, just pay particular attention to the fact that we are very particular about the data type, is it? So it has got to be float 32. This is what OpenGL expects ideally. Okay, so we discussed what this is all about, and incidentally, I think there was a question in the quiz that spoke to this thing that we had already discussed, right? Although the question was really tied to NumPy, and not really what we're looking at right now. Okay, and then in terms of interpreting these different coordinates, our X, Y, Z coordinates, we see that because we're drawing this cube in such a way that the unit of each edge is, each edge is 1 unit. And so if each edge is 1 unit, what we are saying is that we could interpret things like moving half a step in the negative direction as moving to the left, right? If we look at our X, Y, Z coordinates. So if we have -5, it means we're moving half a step to the left. If we have +5, we are moving half a step to the right, okay? To the right of the origin, or to the left of the origin, ideally. And then for the Y coordinate, if we move half a step to the bottom, it's -5, is it? Then +5 would be half a step to the top. In terms of the Z coordinate, using the right-hand rule, we are interpreting these values, the signs, in such a manner that a negative value of half a step means you're moving back, or you're moving further away from the viewer, right? The viewer is you. Just think of the viewer as being you, okay? So half a step means you're moving further away from you as a viewer. And then a positive step means you're moving closer to the viewer, half a step, okay? So in other words, if we were to look at this, I guess when this face comes somewhere around here, you're moving half a step closer to the screen idea, to you, the viewer. Okay, and then we tried as much as possible to try and explain these points. Is it V0 all the way up to V7? There's supposed to be 8 of them. I think when I'm constructing these slides here, I probably have, I don't know if I do, but I should have it should have something that has these vertices, right? To make life a lot easier for you or something like that. There's a slide deck that has something like this, right? This is what we're playing around with. So we see here that V0, we're saying V0 is at the back, right? Bottom left corner, back, bottom left corner, which is here. Anyway, so we set the stage for locations of all of these different vertices. There are 8 of them. And there are 8 of them because some of them are shared, is it? Some of them are shared amongst the different faces. Okay. So this is what I'm talking about here. And then just mentioned here, I think I'd mentioned in the last lecture series that we're using different colors for the front and the back here to make sure that there's a distinction in between the different faces. Make it a lot easier for us to see the transition idea. Okay. Now, there's something interesting about the code that we have, right? What you begin to notice is that we are using what's referred to as index drawing in the code. And the reason we're doing this is it's not possible for us to just simply draw the vertices, right? We have to explicitly tell OpenGL how exactly we want to connect them. Okay, and you notice that the arrays that the approach we're using, index drawing here, makes it a lot easier for us to do that, right? So in essence, what we'll be doing in the code, or what we're doing in the code, is that each triangle is defined by a total of 3 vertices, which makes sense, right? The triangle has 3 points at the end. Okay. So for us to implement index drawing, we have got to indicate the 3, right? The 3 vertex indices associated with each face. Now, if a face is like a square, is it? But the square has 2 triangles ideally, right? And so what we're doing is we are defining this variable cube indices, right, as in NumPy object again, but then we're defining it in such a way that the 3 vertices, or the vertices for the triangle associated with each face, are going to share certain points. If that makes sense. So if you look at the first one here, you notice that the vertex at index 4, right, is shared, right, between these 2 triangles, and also the vertex at index 6, ideally. If that makes sense, right? Walk us through this so that we understand exactly what is going on here. But the idea is that we are going to be using these as indexes to gain access to the things that we want to plot with. It's not really the values that we are using to plot, is it? The values we're using to plot are supposed to range from -1 all the way up to +1, right? These are just indices, ideally. Okay. If that makes sense. So we have a total of 1, 2, 3, 4, 5, 6. Okay. Right. So we've defined a variable, and again, maybe in case this is a bit confusing, what I'm going to do is I will, not that it could be confusing, but so that we're on the same page. What I'm going to do is I'm going to just snip out, it's just, even if it's slow, let's just use Kate or something, right? Let's just use Kate. And I just need this thing here. Okay. So what we're saying is we are defining this NumPy array object. Yes, we have to import NumPy as NP. Yes, we know. Before we use this here. right? So two-dimensional array object here, and we can even check the shape if you want to, right? So we have these 12 entries, right? Each with 3 values, index values right here. 12 triangles, is it? That are going to be used to render or to draw the 6 faces of the cube. Okay. Anyhow, on with it. So we're defining the indices with triangles. And if we check the shape here, what the shape tells us really is that we're defining indices for the 12 triangles, right? And each of the 12 triangles is associated with 3 vertices, right? Or 3 vertex indices, ideally, right? np.int32 is intuitive here. We are storing the indices as the 2-bit integers. These are supposed to be different, or they're different from the actual values we're using to plot, is it? These values here are integers, because in essence, we're going to be looping through. For us to draw using these points, or these vertices, we're going to be looping through using the indices right here, right? So the indices are supposed to be integers. This is why we're defining them explicitly as int32 ideally. Okay. And then again, you notice here that each row is a list of 3 integers that refer to ideally a row of the variable var cube vertices. In terms of how the indices work, for the front face, where the value of the z coordinate is +5, we're going to work with v4, v5, v6, and v7. Okay. Now, if you look at this, right, what we are saying is that, I don't know if I'll be able to draw this here. For the front face, where z is equal to z is a positive value, we are going to be working with v4, v5, v6, v7, v4, v5, v6, v7. Hope this is making sense. Yeah. And then in terms of the 2 triangles that we're working with, you begin to notice here that I want to be v4, v5, v6, v4, v6, v7. So in other words, v4, v5, v6, v4, v5, v6, and v4, v6, v7. So we are splitting it like this. So in terms of the triangles that we're going to be drawing, we're drawing this and this, which is pretty intuitive, straightforward. Really. So this covers the entire square, right, which is on top there. And then for the back face, where z is equal to -5, we are ideally working with the vertices v0, v1, v2, v3. Now notice this, right? The number of vertices that we're working with are obviously going to be 4 because some of the points are shared. But out of those shared points, for us to draw a single triangle, we need 3 points ideally. Okay. In essence, at least one vertex is going to be shared amongst the 2 triangles. Right. In the first case, it's 2 of them actually. In the first case, it's v4 and v6. Okay. And in the second case, it's v0 and v2. Right. So in other words, for us to draw v0, v1, v2, v3, v0, v0, v1, v2, v3, yeah, we have got to render 2 triangles, v0, v2, v1, v0, v2, v1. It's almost like v0, v2, v1, and v0, v3, v0, v3, v2, v0, v3, v2. Right, so it's almost like we're doing this, we're splitting it here as well. Anyway, and then we do the same thing for for the left and the right face, right? So for the left face, because it's on the left, obviously x is equal to -5, negative 0.5. So we are using V0, V3, V7, okay? V0, V3, V7, V4, and then the triangles would be V0, V3, V7, and V0, V7, V4. Really, if you look at it, it's just you just have to be smart in the way that you are defining the triangles ideally, right? And then for the right face, it's V1, V2, V6, V5, and then for the triangles, it's V1, V5, V6, and V1, V6, V2. Anyways, so that's that. And then in terms of how the indices are working here, if we look at the top face, right? What we're saying is that y, well, this is the top face, y is equal to positive 0.5, and then we're using V3, V2, V6, and V7. The triangles will be V3, V2, V6, and V3, V6, V7. I don't know if you'd want us to do this stepwise here. Maybe it would be a lot easier if we do this stepwise, right? Because we did it for the first, the case where you have z equal to +5 and negative, positive 0.5 and also negative 0.5. Let's look at the case where x is equal to negative 0.5 and x is equal to positive 0.5. Because when x is equal to negative 0.5, we are essentially dealing with the left face. V0, V3, V7, V4. V0, V3, V7, and V4. And this can be a bit confusing here because we're looking at this from the perspective of like 3 dimensions, is it? So it's from our viewport, this thing here, this is to the left, right? And then this here is on the right, because this is, but I don't know if you can see here, but well, you can, I guess, right? So this is further to the left, meaning that our x value is negative 0.5, right, for this face here. So for us to render this face, what we are saying is that we are going to have to draw 2 triangles, V0, V3, V7, V0, V3, V7, right? So we are splitting it like this here. V0, V3, V7. And V0, V7, V4. V0, V7, V4. Yeah. Anyways, and then for the positive case where x is equal to +5, the vertices that we're working with is V1, V2, V6, and V5. I'm just going to change this to maybe, I don't know if that's magenta or something. V1, V2, V6, and V5. V1, V2, V6, and V5, which is here. And then in terms of the triangles, V1, V1, V5, V6, V1, V5, V6. We're splitting it, I guess, right? And V1, V6, V2. V1, V6, V2. Is it? So pretty straightforward, right? And then for the top and bottom faces, because we're dealing with y here, when y is equal to +5, we're looking at this thing that's at the top here. I'm just going to use this here. This at the top. So we're going to be working with vertices V3, V2, V6, V7. I think somebody was, I hope I haven't lost connection here. I do apologize. Somebody was attempting to call here and I'm tethering my phone. I do apologize. Wow, this is insane here. Sorry about that. Can you hear me, by the way? I have to log back in here. Yes. Hello, can you hear me? No answer. I guess you can hear me. Thanks for that. Right. So for the top phase, right? V3, V2, V6, V7. V3, I don't know if I changed V3. V2, V3, V6, V7, right? And then for the bottom phase is like V0, V1, V5, V4. V0, 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 V1, V0, V1, V5, V4. Now, what you notice here is like, this can be a bit confusing. It's like, wait a minute, Lighton, how is it that all of a sudden, I don't know if you're thinking about this, right? All of a sudden, the Y is this, right? It's dimensions here. It's all Z. We've kind of, in 3D, the way that we're viewing the Y here is like, this is the Y, and this is a positive Y, is it? Positive values of Y, and then the negative values of Y will be here. If that makes sense. This will be a negative values of Y. I don't know if this is making sense here. But anyways, what is important here is to appreciate, I think we just need to appreciate exactly why we are using index drawing for us to render this. And we'll go through the code just now so that we are all on the same page, I guess, or something like that. Right? Just illustrating how the triangles get to share the points, is it? I just have an example here of a face comprising of 4 points, V4, V5, V6, V7. And we see here that, triangle 1 is going to be drawn using V4, V5, V6, right? This. And then triangle 2 is going to be drawn using V4, V6, V7. This is what we are doing for all our 6 faces, ideally, right? 1, 2, 3, 4, 5, 6 faces. Good stuff. Now, there's more here, right? For us to make each face a different color, which is what we have here, by the way. For us, for us to make each face a different color like this, right? We have 6 different colors we're playing around with here. What we are saying is we are going to define these colors. And we're defining these colors using, this is just a normal 2-dimensional list ideally. It doesn't have to be a NumPy object in this particular case. Or you could define this as a NumPy object, right? But what we're saying is we're defining an array or a list, Python list, that will hold 6 elements ideally, right? And each of these 6 elements is also a list with just 3 values, right, correspond to R, G, and B ideally. And in essence, when we are drawing, what we're going to be doing is we're going to be referring to these things here, right? So we want to draw, the face, the first face, which is supposed to be red or something. So all of the 2 triangles are going to be drawn using this color, ideally red, if that makes sense. Maybe when we look at the code holistically, it will make sense. I don't know. Right? So we're using a Python list, right? So each inner list will contain 3 floating point values corresponding to R, G, and B. Okay, and because we're just using very simple colors here, the common colors that we're used to, red, green, blue, magenta, cyan. The last 2 are just, they're derived from the primitive colors R, G, and B ideally. Anyway, so the idea here is, what you notice when you start looping is that the order of the faces are supposed to match the order of the 12 triangles in the index. Right? So, for instance, the first 2 triangles, right, will be at the front, and then the next 2 will be at the back. That's what we're doing. Okay, so the question then is how do we implement this drawing function, right? Because fundamentally we're supposed to implement a drawing function that is going to refer to a couple of things here. It's meant to refer to the coordinates, okay? The coordinates, and the way it's going to be referring to the coordinates is we're going to be using indices. If that makes sense. Let me just do this. Oh, I shouldn't have. I'm just going to leave it here. I think we have it open here. Here. Oops. I don't know what's happening here. Okay, there we go. I have no idea what is happening here. I don't know what's happening here. There's something off. My thing is not responding all of a sudden. I don't know why. Oh my goodness. Oh, there we go. It just crashed here. Hopefully to be accessible now. There we go. Right. So we are essentially going to be using these things here, right? To get what we want is the point I'm trying to put across. Let me go back here. Okay, so the drawing function, very simple. You will see here, right? Boom. And so what we are doing is we are going to be looping, right? We're going to be looping. So for each, remember we have 6 faces, right? And I'm just using the range function. I don't know if you remember Python here. The range function, when you feed it one value without specifying the step value, what it does is just is going to start from 0 and then go all the way up to the value you feed it -1 ideally, right? So if you remember your Python, they told you that if you do range 6 here, you're going to have 0 to 5, is it? You may not really see 0 to 5 here, but if you say for var item in range 6 here, if you print var, you're not going to print the 6, right? You're just going to print 0 to 5, which is fine for us because it's almost enumeration starts at 0. We're going to have what? We're going to have 1, 2, 3, 4, 5, 6 faces. Okay, so we're saying for each face, right? For each face, 0 through to 5, what we want to do is, because if you remember when we're drawing, remember we're drawing triangles here. When we're drawing triangles, the first thing we have got to do is specify the color that we want to use to draw the triangle. Okay, so as we are looping for each face, we define the color, right? And we're defining the color using GL color 3F, right? It's going to accept 3 values, if you remember. RGB, which is pretty intuitive. Now, if you remember here, what we're doing with this notation is we're unpacking, is it? We're saying we want to unpack. The values associated with this face. We want to unpack. Observe. In here, we have var face colors. This is var face colors, yeah? Right? var face colors is just a multi-dimensional list, is it? There are lists within a list, right? If we get, when we're looping through the first face, which is at index 0, we're saying we're going to get a list that has red, is it, as a color. Now, this is just a fancy way of, we're just trying to make the code more elegant here. I don't know if it's going to be confusing to you, but this notation just unpacks these values because GL color expects 3 parameters, right? Yes, it expects 3 parameters. So when we evoke I'm gonna go back here. When we are saying we evoke this thing here to set the color for the face, if we don't do this, right, this will not work. It will be GL color 3F. If we don't have the asterisk, it's going to have this here. Right? So what we're doing really is we're just unpacking. We're saying we want to unpack. And I guess, I don't know, maybe you'd want to do this the more the more and I'm trying to think of a more, I guess, an approach that would probably involve a series of additional steps for you to get the values. What we want is 1.0,0.0,0.0. For us to do this, we just use this notation where we do that. And you can check this if you want to. This won't work, by the way. If I just say I want to unpack this, it will fail. However, if I say I want to unpack this into, we're unpacking this into a function, is it? I can do something like this, right? So if I unpack, it's going to be something like this. Don't know if this is confusing or not. I mean, you can rewrite this if you want to. You can rewrite this in such a way that you're saying when you get this, I don't know how this would be done here. We can write it like this, is it? We say 0, comma. This is retarded, really. Sorry about that. This is very mad. But you know, I mean, if this works for you, you can do this. So when we are feeding this to this GL3F function, I'm just going to do this, by the way. Say import OpenGL.gl, I guess, asterisk from this, import everything. Listen, we want to do this, right? This 3F. We're using 3F, right? Now 3F, if we feed it this, it will fail this. Right? It will fail because it accepts these arguments. But if we say we are instead going to feed it, because we've already gotten it here, we are going to feed it. I think I don't know if I have face colors done, probably not. This is insane here. I'm just going to do this and just come up here and showcase to you that this will work. You do this, we're saying you can do this. This is what is going to happen. Right? If you replace the code that does the unpacking and you do this, this will work as well, is it? So we can in essence feed this and it will work. If you want to do it this way, I don't know, you can write your code. It's a nice way of practicing, right? The other interesting thing to do here is like, and I was expecting people to maybe tell me this. Oh, but wait a minute, Lighton. We have do we not have V3V, right? Yes, we do. It's just that the code I'm using here, I mean, I don't want us to touch on the vector variants of these methods, but you could do this. And when you do this, you just feed it this. It's going to work as well. So what I'm saying is that in here, the code that we have here as this could also be replaced as 3FV, right? And then you just do this without unpacking. Boom, it will work. Is one option. If you want, you can do this in such a way that you again use GL colors. Come on, colors 3 like this. But what you're going to do now is you're going to use this variable without unpacking, without asterisk. However, what you're going to do is you're going to say 0. But this is just, nobody writes code like this. I don't know. I'm writing it like this. Do this. Right? So different ways of doing this. Anyways, So back to our code, right? Pretty straightforward stuff here. We're unpacking the colors, so we're defining the colors as the first point. Notice that this drawing code construct that we have here is wrapped in between the GeoBegin and GeoEnd functions, yeah? And we're drawing triangles. Because we're drawing triangles, we are first of all specifying to say we're going to be drawing these triangles in such a way that we're drawing triangles for each of the 6 faces, so 6 times. The first time, for the first face, we're going to draw 2 triangles that are going to be drawn using the color red. Okay? Now, when we define the color here, what we're going to do is we're going to loop 2 times, is it? Range 2 is going to loop index 0 and 1, is it? Range 2 for var I in range 2. If we do print var I, it's just 0, 1, right? 0, 1. So in other words, we're saying we want to draw the true triangles associated with this face that we're looping through. And how are we doing this? Well, we first of all have got to get the indices associated with that triangle. If that makes sense. Now here's the thing here. You'll notice that what we are doing here is we're saying we're going to get var face, right? Which in this particular case is going to be 0. I don't know if you're following through here. Var face in range. The first time we're doing this, var face is 0. So it's like 0. var I is also going to be 0, is it? Right? So it's almost like we are saying var tri is going to be equal to var cube indices 0. Right? And this will make sense because the way we're drawing these things here is that the indices kind of give away the triangles associated with each of the different faces. So the first face that we're working with here, right? For the first triangle is going to be in var underbar cube indices 0. Now, I want to draw attention here to this. This. Jesus. var index 0, boom. So in other words, it's like the way we are looping, the way we've constructed the loops here is in such a way that we are going through these in sequence. So we're going to start by drawing this, right? In here. So we get the index, and then we are saying we now want to, because the index is going to, the index tells us it tells us it gives away what values are we going to use to plot the 3 vertices associated with the triangle we're looping through. So we loop again, is it? This time around we are looping in range 3 because we want to loop from 0, 1, 2, the 3 points that will enable us to draw the triangle, right? And then what are we saying? We are saying we are going to loop through var underbar cube vertices. So we are going in here, and we're going to loop from 0, 0, 1, 2. So when Vj is 0 here, it's almost like we're saying we get this is going to be, wait a minute here. var try, let's loop through this one at a time here. We have confused things. Just going to copy this here so that it's a lot easier as we are looping through. I think when we look through this once, you should be able to get the idea, I believe, I suspect. But why again? I'm just going to go here and go through the loop here. I don't know why I'm doing that. It's going to be a lot easier if I do this. Right. So if we start looping this, we can go through this one step at a time, I guess. The first time we're looping through here, varface is equal to 0, right? Right. Range 6 is 0, 1, 2, 3, 4, 5. When we come here, I'm going to put it here, I guess. I don't know if it's going to be confusing here. Maybe not. Should I put it on top? I don't know. Or I can put it, I'll remove these comments, actually, the ones that were there before, so it's a lot easier. I don't know what this is here. So it is a lot easier like this. So the color is straightforward. We know the color we're drawing here is going to be GL color 3F, and then we have we're essentially going to have this, is it? It's this. This is fine. Red is what we want to print like that. And then when we get here and we are looping through the two triangles that we want to draw, we are saying var I is equal to 0 in the first loop. When we get here, this is where we had the confusion here. Var tri is going to be equal to var cube. It's going to var cube under bar indices, is it? At 0, because var face is 0, var I is 0. So it's like 0 plus 0 is 0. So in essence, we're saying we want to get the value, the values associated with var under bar cube indices at 0. Sorry, I'm moving around here because I'm hoping that this is going to make sense here for you. The one that is at 0 is this value here. So in other words, the output here is going to be this. And then when we come here, we want to loop 3 times, right? The first time we are looping, var j is equal to 0, which is fine. And then when we come here, I think this is where we had the confusion or something. We're saying we want to get var under bar cube vertices by getting the value in var tri at index 0, 0, 1, 2. So in other words here, var v is going to be equal to, right, 4. Now, if this is equal to 4 here, var v is equal to var v is equal to no, so this value is equal to 4. So var v is going to be equal to, sorry again, this output here, var under bar tri for index var j is going to, this entire thing here is going to be 4. So if this is 4, right? If this is 4, what we are saying is we want to get, this is going to be equated to the list of the array associated with this thing here at 4. If that makes sense. I'm going to go here, var under bar cube vertices, var under bar cube vertices, 0, 1, 2, 3, 4. Right? So it's like we're getting this, yeah? This var under bar v, I don't know, replace this, I think. It's going to be a lot easier. Or can I just do this? I'm going to zoom out here. So it's like v under bar v, var under bar v is going to be this array. Right? And so for us now to actually draw the point, all we are doing is we're going to say we want 0, 1, and 2. Just this. That's it. Now, you know, it's like, why are we doing this? Well, index drawing, it turns out, is much more efficient, right? If you want to try this out, what you can do is you can do this. There's a couple of different ways you can do this, right? You can say, I'm going to be, if you think this is confusing, actually, what you want to do is you want to try this out by doing it stepwise, right? this is too confusing. Right? What you can do is you could say, I'm still going to look through the faces, the 6 faces. This is going to be tricky here. But for each face, once I specify the colors, what I can then do is I can draw the true triangles manually, if you will. But then again, it would be pointless, right? You wouldn't be able to elegantly look through this, because what we're doing here is, you look at the lines of code, right? Very few lines of code, and all we are doing is we're just looking through here. We want to, first of all, print the red colors here, right? These. That's it, if that makes sense. I don't know, maybe not. Is this making sense? Or it's a bit it's a bit confusing. What I can do is, or what I will do is, I'll try and see if I'll let you play around with this. Right? We've looked through just one triangle, and if you want, we can go to the next triangle. Is it? Because in we can go to the next triangle if you want to, but I mean, it's just a waste of time. We're just looping and doing the same things over and over again. But the key thing here is to appreciate the fact that we are drawing these things one face at a time, per face drawing, right? And because we're doing per face drawing, each face has 2 triangles that have the same color. Each face has 2 triangles, right? And for each triangle has 3 points, is it? Three position attributes, X, Y, Z. 0, 1, 2, X, Y, Z, X, Y, Z, 0, 1, 2, 0, 1, 2, 0, 1, 2. That's it. I guess, I don't know. I don't know if this is making sense here. I'm gonna let you go through the code, and then when we have our class on Wednesday, I'm expecting a whole lot of questions, and I'm expecting people to maybe try and modify this in such a way that perhaps it's not as simplistic as we've currently designed it, right? It's by design. We're trying to showcase a number of different issues. Yeah. And what I have here is just a step-by-step explanation, the things essentially that we were talking about, right? We don't have to repeat these things, why I'm using the asterisk, the variables, and what they're going to be, what value they're going to hold ideally as you're looping through here. Okay. So this is the things that I was explaining. So the question is, why would we be using this approach, right? Why not do it manually the way we've been doing? Well, it turns out that right? So we are separating the indices that we're using, the colors and the vertices, from the actual drawing logic. And it turns out that this is how core OpenGL actually works with buffer objects. And we're not really going to look at buffer objects. I was almost tempted for us to do this, but we're not going to do that. We are using immediate mode, right, or legacy mode, ideally. And also we wanted to demonstrate exactly how NumPy arrays can be used to store and index vertex data efficiently. And then what I have in the module file itself, the .py file, is you'll notice that I've encapsulated all of this logic into a function. And the idea is where we were evoking the draw function for triangle fun, those points and stuff, we can just replace this function. So everything else is the same. The only difference is going to be the draw function for the cube, which is this. So we're wrapping everything into a function, ideally. And really just to mention here that when you run this, you see a smooth rotating cube, which we've already seen. Yeah. You see this smooth rotating cube, right? Where each face has a distinct color, right? Those colors that we defined here, 6 colors. These 1, 2, 3, 4, and this is 5, 6, right? 6 colors. Okay, so something that is akin to what you're seeing here. Again, just explaining this image here, the cube, our cube is centered at the origin. Right? Each face has a different color. We have 6 colors. And then depth first testing ensures that the faces closer to the viewer hide those behind them. And this will make sense once we look at transformations, which is in the next lecture series ideally. So the rotation, around the diagonal axis, it will review all the 6 faces, making the 3D structure clear ideally. And again, this is like, it's on a 2D screen, is it? But we have this illusion that this thing is like a 3D object again. Again, just an explanation of the code relative to what we had started explaining here, right? The vertices or the vertex data would define the 8 corners, right? 8 points V0 to V7, if you remember. Our index array, the variable V underbar cube indices will specify the 12 triangles. Is it? Some of those things are shared, the points are shared, right? And then the per face colors, or the colors that we're defining in the variable var underbar face colors here, are iteratively set within the drawing loop itself. And if you look at the code, what you'll notice is that we achieve this rotation using a new function that we haven't yet discussed. We're going to discuss this in the next lecture series, called GLRotateF, ideally, right? Yeah, so this simple example contains all the core ideas of vertex specification, right? The attributes, primitive assembly, if you remember these discussions that we had. And of course, what we're going to be discussing in lecture series number 6, which is basic transformation, right? In this particular case, we're just using rotation, ideally. And this will make sense in the next lecture series here, where we're going to study these transformations in depth. Now, I want to leave you with a few things here in terms of homework, and you want to do this, right? It's like we've implemented our logic using G underbar triangles, but if you actually seriously think things through, you will notice that, well, this is not really very optimal, is it? When we're using GL underbar triangles, we need to render 12 triangles, right? So that's 2 triangles for each of the 6 faces, so 2 by 6, which is 12. And each, right, of those triangles has 3 vertices, right? So it's 3 times 12, which is like 36 cores, vertex cores ideally. Even though some of the some of the points are shared, but every time we are doing a GL underbar triangle, we are sending to the GPU vertex cores to render the triangles. So it's like 36 of them, which is not really optimal, is it? This is suboptimal. Yeah. So, but the question is, can we play around with some of those things that we discussed, like GL underbar triangle? I don't know how much of this you remember here. Can we, come on. Can we do this? G underbar triangle, this. Remember this? Fun and strip. So can we come up with an implementation which arguably perhaps is going to be more efficient at rendering these triangles? Okay, so I'm going to leave you at this. This is homework for you to. This will force you to play around with this. You want to make sure you understand what's going on here and come up with implementation, right? And then what I have here was just an explanation, just for those of you that may want to be ahead of the pack here. It's like, how is this rotation achieved here, right? You'll notice that there's some code snippet here where we have strange things that we haven't discussed here, like geometrics mode and geoload identity, and more importantly, GeoRotate, right? We're going to discuss this in the lecture series, but this is us telling you that the rotation is actually accomplished by this code snippet here, and you will find it underbar matrix. Ooh, Q. I don't know why I'm used to doing this when people have been complaining and say, open using Kate or something. all of the rotation is accomplished by just this code here. Isn't that cool, right? Just this. Okay. Anyway, so we're going to be looking at these affine transformations in detail. We'll look at the theory first, and then we'll look at how these are implemented in OpenGL. It's going to be a lot of fun, right? We're going to focus on translation, rotation, and scaling, but just mention that, you know, there are other, you know, transformations as well, like sharing and, you know, reflection, right, and stuff like that. And hopefully some of the things that we discussed during our discussion of the logical graphics pipeline will actually make sense here. Now, something else I want us to do here is it's like if we can accomplish this, right? If we can draw, there's no rotation, but if we can draw something like this, can we draw some funny representation of our, back to our polyfield case study? You know, if we said wanted, by the way, it's supposed to like kind of represent the soldier. The soldier is like it's a complex object ideally, and you wouldn't really draw it using the primitives, right? The GeoUnderbar triangles. There's like an end user application that you're doing, just like when you're building an application, a desktop application, GUI-based application. They told you if you were told to build something like this, there are buttons, there's panels, there are menu items. If you're doing Java in this, nobody's going to. They told you this. Dr. Nyenda, I think, is the one who was teaching you 20. I've forgotten that. 2010 or something. They told you that you don't write the code, right, at a very low level, right? You drag and drop, is it? You use tools that can simplify this. So you'll be dragging panels, and then you get the point. There are frameworks that you can use, right? It turns out that the same applies. If we wanted to create the equivalent of the polyfield soldier object, we could probably use something like Blender, right, or Unity actually, which makes life a lot easier. But assuming you wanted to draw the polyfield soldier using these primitives we've discussed, I have homework for you. Can we draw something like this? Right? So we have the gun here, you know, we have these legs, right? And the limbs here, and the head, and the torso. You know, let's try and see if we can play around with this. You know, you notice that what you're doing when you're drawing the head is going to be the same as what you're doing when you're drawing the torso, is it? The only difference here is that the head is made up of edges with the same length, right? The same unit length. Whereas the torso is obviously, the side here is going to be significantly larger than these sizes. The same applies to the limbs, right? The limbs, the hands, and probably the legs or something. Okay. So please try it out, right? It's going to be fun. I'm sure you will enjoy this. Just to put things into perspective here, before we put things into perspective here, in the next lecture series, we're going to start our discussion of transformations beginning Wednesday, right? We'll focus on translation, rotation, and scaling, and we'll start off with the theory so that we understand how things like geo-rotate 3F are going to be working or something like that, you know? Yeah, so in terms of what we did in this lecture series, really, we first of all started off by reminding ourselves about vertex attributes. There's a whole range of attributes, if you remember. Although after that discussion, we were mostly playing around with position and the color, right? We didn't really touch on the normal and custom attributes and stuff like that. Okay. And then we had an outline of how exactly go about specifying 3D vertices in OpenGL using immediate mode. We have explicitly made mention of the fact that we are going to be using immediate mode because our interest is to understand, how these API calls are actually done, right? We're not really interested in writing these shader programs using modern day OpenGL programs or code. And then we had a discussion of those drawing primitives, the primitive types, if you remember, points, lines, triangles, right? This was interesting because I think from the outset, we kept on mentioning that the smallest unit that you can send to the GPU is a triangle or something. But funny enough, we're able to draw geo points and geo lines and all those things. Well, I did mention that you could be using this for other the package itself, or the API could be using it to render other things, right? However, it doesn't take away the fact that the GPU is actually optimized to process triangles again. Anyway, and then we went through, we tried to put all these different concepts together, this idea of drawing primitives by rendering a 3D cube. Okay. Anyways, I just realized I had a request from the course to say the GitHub repository is not updated. I'll push the changes. I just have to push actually. So I'll issue a push command right after class here. But what I've done here is I've just included these Python module files that are referred to in the slides, just so it's a lot easier for you to follow through with what's happening. I'm gonna pause here and ask or find out if there are any questions associated with what we've done in this lecture series, which is Vertex Specification. Don't know. You can kind of think of what we are doing here as, if you look at the logical pipeline here, is we're in model space, right? And we're rendering these objects. Ideally, these objects are made up of meshes. Your meshes are made up of triangles and stuff, right? The triangle is made up of, an edge, and then there's faces and stuff. An edge is made up of a point. Okay. Next up, we're going to go into world space and see those transformations. Are there any questions? Please don't ask me, but why did I major in software engineering? I don't know. It should be you. Okay, so if there are no questions, let me just check in the chat here. There's usually questions. Sir, there are people who were unable to join. No, but I allowed everybody else here. So some 30 minutes ago. I use this plugin here called nobody's waiting here, called this auto admission or something like that. Guys, thank you very much. Have fun. Have fun with OpenGL or PyOpenGL. You guys have fun with OpenGL. No questions also. Remember that the quiz is next week of Friday, not this week Friday, but next week Friday is actually going to be based on this lecture series. Go through the homework questions. Thank you, and enjoy the rest of the Sunday.
All right. Thank you.